those of you who are near, one of my tie tacks is one of those original cracks from that program. So I was then faced with managing a program and making sure all the data was correct before we destroyed the specimens. The cracks were generated by initiating a fatigue crack, an EDM slot, throwing that crack from that EDM slot in fatigue mode, and machining off the EDM slot. So we had a tightly closed crack in an as-machined panel. And that was what we presented for the first inspection go-round. Now, by changing the shape of the EDM starter, we can change the shape of the crack that is grown. And by changing the mode of crack growth from bending to bending and tension, we can control the shape of the crack. So we had varying shapes of cracks, but the parameters that initially were input was we needed to know how long the crack was by the ND technique. So we had approximately 1,000 observations for each of these inspection sequences. And all I had to do was reduce that to one number that the fracture mechanics people could use. And all the cracks of the same size don't respond equally. All cracks are not created equal in terms of NDT response. So the small cracks can give big signals or small signals. So we have a spread. So we've introduced a variance in the detection process. There are many others. But the bottom line was that it had to be reduced to a single number. Ideally, we always try to plot our data in some form to understand it better, and we did that by several different techniques. But there had been some pioneering work done during World War II by a couple of people at MIT, Sweats and Tanner, John Sweats and Tanner. And they were trying to determine how good the radar operators were. And so their pioneering work was one of the things that we used. We did a lot of research or a lot of literature search to try to see if anybody was doing anything like that. Now, unfortunately, they didn't work the statistics part of it. They simply worked how do we present the data, and they originated a term called probability detection and probability of false alarms. They plotted those on the same relative operating characteristic curve chart that I'll show you a little later. But that chart and the way they plotted that chart can also vary by the acceptance criteria that I put on there. And secondly, the problem that they were working was not quite what we were faced with in the ND area. They had a whiteness, but they also had a size, but they also had a moving target. And for any of you who are old enough to remember when we looked at X-ray film, if you see a gray hair looking at X-ray film, he never keeps the film static. He always vibrates the film or jostles the film a bit because the human eye is better triggered by a little bit of response there. So it wasn't exactly the same problem, but we needed to, once again, reduce that to a single number. Since we were dealing with a material or a acceptance criteria that would be used in the design of structures, we wanted to make sure that we were in concert with Mill Handbook 5. And Mill Handbook 5 is the Bible, was the Bible, and still the Bible for the way you generate material properties, simple material properties of ultimate strength, yield strength, and elongation, and so on. And those are always reported at the 95% confidence level. And what that means is that you have to have a large large number of specimens, and it tells you the distribution of different production lots that you have to have in order to generate a number, and then we can put in a handbook and say, this is what you'll use for the design. Well, even with 1,000 observations, we didn't have enough to plot the data at a 95% confidence level. So we stepped down one and plotted at a 90% confidence level. And a 90% confidence level says that statistically, if you have 29 successes out of 29 opportunities, you have a 95% confidence level that the true value is between whatever you measured at that point and 100%. So we just, I'm sorry, I said 95%, that's 90%. If you have 29 out of 29, it is indeed 90%. So we used what we call a moving average technique. So we ordered the cracks from the largest to the smallest. We counted down 29 observations. We calculated the number of finds over the number of opportunities, and we put a point on the graph. We dropped off the largest crack in that group, added the next smaller crack in the list, recalculated, put a second point on, and continued to do that until we ran out of data. So that then generated the first POD curves, and that was by what we know, then do, and still do, as the moving average technique. And it is a binomial technique, and it is rigorous, but it takes a lot of data. And this is one of the POD curves from the original program. And I'm showing this to you to help you recognize the agony. This was in the days when we had mainframe computers. We had to input our data and our program on punch cards. There were no debugging tools. It required an overnight processing time. My contract, this was in 1970 time frame, my contract got charged $500 for every one of those curves that we generated, whether we had a goof in the program or whether the computer goofed. And so it was tedious times. I now do that on my laptop that I have in my case in about 30 seconds. So we have made some progress, and that is, indeed, we don't need to quantify it, it's just good. Okay, the second task we had now, we generated a POD curve. What number did we report? And we looked at the data, and where all of the curves started near 100%, and then came to some point and started to drop off rapidly, what was the inflection point of the curve, we noticed that that was characteristic of all of the data and all of the curves that we had generated. So Bud Kastner and I, and one of my statisticians, sat down over a beer one evening, and we said, we're going to report the point that curve goes through the 90 percentile of it. And that's where the 90 percentile comes from. And that's a convention. No solid thing beyond that other than there are reasons to pick that point that you can analyze ad nauseum. Secondly, we were concerned that that number V is near the 95% point. And so once again, from Mill Handbook 5, you can predict, based on your success rate at that point, what the lower 95% confidence level is. And the point then that should be used and should be go into the calculation is the point at which the base POD curve went through the 90 percentile point, the lower confidence level that was calculated for that, and that's the number then that we reported as the 90-95. Now, how many in the room have heard of 90-95 before? How many of you recognize this is where it came from? Okay? So, it goes back to Mill Handbook 5, and that's the basis for it. And it does depend very much on the sample that we test. Now,